How do stress trajectories reveal component load paths? Imagine trying to follow the flow of water in a river. Stress trajectories do something similar inside a mechanical part. They show us how internal stresses move through the material. When a component is loaded, different parts experience different stresses. These stresses are represented mathematically by a stress tensor, which includes normal and shear stresses acting in various directions. The principal stresses are the normal stresses where shear stress disappears, and they act along specific perpendicular planes. Stress trajectories connect points in the material along these principal stress directions, forming continuous lines. These lines are like maps that reveal how the internal forces travel through the structure. By studying these paths, engineers can see where the highest tension or compression occurs and how the load is transferred from one part of the component to another. For example, in a thin plate under tension, the stress trajectories will show the main paths where the tension flows. This helps in designing reinforcement by placing stronger material along these routes, making the structure more efficient. In bending problems, the trajectories show how bending stresses distribute across the component, guiding where to add stiffening elements. These paths are also the basis for simplified models like strut hand tie, which break complex stress fields into basic load-carrying elements. Struts handle compression, while ties handle tension, and both follow the natural load paths shown by the stress trajectories. Overall, stress trajectories are a powerful tool because they visually demonstrate how forces move inside a component. They help engineers understand the flow of stresses, identify critical areas, and design more effective and material-efficient structures. By aligning reinforcement and structural features with these natural load paths, mechanical engineers can improve performance and safety. Using stress trajectories in stress analysis makes it easier to predict how a part will behave under load and ensures that the design can handle the forces it will face during use.